from Hamlin Center and Robot Intelligence Lab, Imperial College London, and today I'm presenting our work on augmenting neural network for full robot kinematic modeling in SC3. Robot kinematics is a very important basis for robotics as it allows mapping actuation or joint space to Cartesian space, and having an accurate model ensures precise motion control and reduces the need of costly external sensors to compensate for motion errors, which can not always be employed actually. And generally, articulated robots are described through the Hardenberg convention. However, new advances in the design and requirements have led to an increasing complexity in robotic systems. And for this reason, artificial neural networks can help building complex robot models. Artificial neural networks have generally been used in two different ways for robot kinematic modeling. It's either inverse kinematics learning or forward kinematics learning. So when learning the inverse kinematics, we can directly obtain the control variables given a desired pose to reach. The problem is that this mapping is generally not univocal, especially for redundant robots, which means that to a given desired pose, there exist multiple solutions for the joints or actuation values. And also the control output only relies on the acquired data, and for this reason it's hard to exploit redundancies in the control. While learning the forward kinematics, instead, the mapping is generally univocal, and also the learned model can then be used in standard and consolidated optimal control techniques. The main problem is that it requires the computation of the robot Jacobian, of the Cartesian Jacobian for control purposes. Another aspect is that, when learning the position, so for forward kinematics, this process is pretty straightforward. And for orientation, instead, there are multiple representations like angle axis, uniquaternions, or roll pitch and angles. And each of these representations has been shown to be discontinuous and difficult for artificial neural networks to learn. Additionally, angle axis and quaternions require unitary axes. For this reason, a prepared learning strategy or a higher dimensional representation is needed. So what we present in this work is Augmented, which is an augmented neural network with differential relationships to learn full robot poses in SC3 for Cartesian position orientations. Because of the discontinuities in the orientation, what we propose is to use a trigonometric representation for learning orientation, and in this work we focus on roll, pitch, and yaw angles. And we use 4 different cells, so 1 for learning directly the 3D position, and 3 for learning each trigonometric representation of the roll, pitch, and yaw angles. And also, Augmented includes differential relationships during training for each mapping, which are shown to improve the performance of model learning. So in our architecture, each cell is trained independently, and we have 2 different losses, so 1 for the position and 1 for the orientation. And in both cases, losses are a sum of 2 terms. So one term, which is, let's say, on the original level, and another term which is instead on the differential mapping of either the position or the orientation. And it's possible to directly extract these Jacobians from the network architectures. And for the orientation, instead, since we're learning this trigonometric representation, we also add a regularization term to make sure that the trigonometric equality is satisfied. So once the model is learned, so again, we are learning like this trigonometric representation, but it's possible to directly extract the angles and so obtain a full robot pose. So during control, we generally specify a given trajectory, specify in terms of position, roll, pitch, and angles. And so the control variables can be easily computed with the learned model from a simple minimization problem. And also in this case, the robot Jacobian can be easily and analytically computed from the learned model and from their geometric representation. So we tested our approach on different robots, so a 7DOF arm and 3 segment soft robot, We collected data by exciting the robots with random motions in order to explore as much as possible their workspaces. And we performed two different tasks, so a path tracking test and a regulation test. So these examples show our approach compared to a standard feed-forward network, which doesn't include any differential relationship during model learning. And this is for the 7DOF on this infinity shape path. So what we show is that our results show that our proposed AugNet works well in modeling, both for position orientations, and also adding this differential relationship during training helps improving model learning and also control compared to a standard feed-forward network. We also tested on the soft robot, again on this infinity path, and yeah, we also show that also in this case our network performs better than standard feed-forward network, especially in case 4. You can see that the standard feed-forward network just diverges and leads to a very unstable behavior of the robot. These are the overall results on the soft robot. And again, as mentioned before, we achieve better performances by including this differential relationship during training. During the regulation task, instead we specify different poses for the robot to reach, starting from the original vertical configuration. And in this case, I mean, we still have some failure cases. And this is because, I mean, generally these random poses may end up being in regions that were little explored during model learning. Again, these are the overall results, and we show that in general our approach outperforms the standard feed-forward network model learning. We then finally run our experiments on a KUKA arm. In this case, I mean, all the controls is done in free in an open loop, so there's no feedback. And also in this case, on the real robot, we managed to achieve a good tracking accuracies on 2 different paths. So in conclusion, our simulation real-world experiments show that our proposed AugNet outperforms standard feed-forward neural network learning approach. Raw picture and angles have been used for control, so it must be assured that the desired commanded values are continuous to avoid stability in the control. Further investigation is needed in order to properly propose a representation for quaternion or angle axis representation. And also, as mentioned, there are still some generalization issues due to the fact that generally some poses may end up in regions that were little explored during training. Thank you for your attention.